admit it. Those last two videos were too long. I got carried away. Can I get an amen? Well, I'm going to try to keep things a little tighter moving forward, keeping these videos less than 20 minutes. There's just so much to say when it comes to diamond. Roman numeral 3 is going to be color and optics. We're starting to get now into the value of diamonds. Now we're going to rely on Smithsonian images here. This is going to be our image to discuss optics of diamonds. This is called the Pearson diamond, and this is the diamond that the Smithsonian uses also to discuss diamond optics. Let's go through optics first. Optics are one of the primary reasons for diamonds' value. The other is the genius of marketing that's been behind diamonds. But diamonds really are a special mineral that have fantastic scintillation, brilliance, and fire. And these are the things that are going to be controlled by the natural conditions of the diamond, but also the faceting. So we're going to say that the optics are controlled by natural properties and cut. Properties and cut. And by cut, I just mean how the faceter went through it. Now, of optics, we're going to start with scintillation. Scintillation is the sparkling brilliance of a stone. And this is primarily controlled off of a light reflecting off of facets on the surface and also in the stone. So we're going to say that this is mostly a reflectance effect. So this is controlled by reflectance of light. And importantly, light that is not allowed to escape the diamond. Reflectance of light not allowed to escape. Now, when we think about light being allowed to escape a diamond, we should be thinking about refraction, not necessarily reflectance. But of course, those two work together. Now, underneath scintillation, we need to talk about the refractive index of diamond and critical angle. Refractive index. And we've learned about what these are in the past. But refractive index is how light is bent when it enters the diamond, right? So if here is our faceted diamond, and light is entering the diamond, it's going to bend, right? The angle of incidence is not the angle of entrance into the diamond, right? This is refraction. And so this is our measure of bending of light. And for diamond, it's very high. It's 2.417. So that means diamond bends light extensively, and it creates a critical angle that is very low. Critical angle that is very low at 24.5. So that means any angle greater than 24.5 cannot escape the stone. It will come and will bounce. And it will bounce, right? And you'll just keep getting reflections off of the different facets to create our scintillation. That is how that one works. Now let's move to brilliance, okay? This is kind of how shiny the stone looks. And this is controlled by the luster. So we're going to go brilliance controlled by adamantine, which is the highest level of luster. Really, the adamantine luster also itself is controlled by 10 on Mohs hardness scale. When something is very hard, it can take a polish very well. The more polish it is, the more the light is going to reflect, even when it should enter the stone. So I don't want to get confusing here, but basically, this adamantine luster will reflect 17% of light that hits the stone. When light hits glass, only 4% reflects. So let's say, so it's gonna say 17% of light that should refract. Okay, basically enter the stone or exit the stone. That should refract doesn't because of luster. This is opposed to only 4% does this with glass. So its luster is very important in terms of how shiny and sparkly the stone is. Now the last thing about diamond that's really so spectacular is its dispersion. And dispersion is the difference in index of refraction 2.417, but for red light versus ultraviolet. So what dispersion does is it creates fire, and it makes white light break into its different components like red and greens and blues. So I know we've talked about it before. We're going to go over a little bit right here. That is the dispersion of diamond is very high. So and diamond dispersion, we also call it fire. Fire equals dispersion. Now remember, Roy G. Biv is our rainbow, and all of those combine together to form white light. But the refractive index of diamond for red is 2.407. Now the refractive index of violet is 2.451. The spread here is very big, and that is what our dispersion is. So the dispersion is the difference in refractive index between red and violet. So we're going to say that dispersion is very large, and we just subtract those two numbers from one another, we get 0.044. It's one of the highest of any of the minerals. So what this means is when light enters our diamond, it shatters the light like a prism does. So what we can do, let's draw this like this. Oh, and if you have multiple colors, you should use it. I'm going to draw, yeah, I can do it, I guess. So we're going to have red, so white light comes into our stone like so. And then it starts to break apart. Or, oh no, red. I want that to be red. Red goes here, and then, can I make this purple? Yeah. And then violet goes here. And then when it's above the critical angle, so it reflects, and it'll go like so, and red will go like so. And as your travel distance increases, so travel distance increases, so does color spread. When the colors are really close together like they are right here, our eye might not differentiate them. But as the light continues to get bounced around, the colors get further and further apart, so eventually when it comes out to our eye, we see pockets of red, and we're going to see pockets of blue that are visible to our eye. Okay, this is why we see dispersion. So the light breaks up into a rainbow. That would be another way to say this. Light breaks into a rainbow. It's all caused by the difference in refractive index of red and violet light. Now for CZ, one reason why CZ is such a good diamond simulant is because it actually has a very high dispersion that's even higher than diamond. So if you see something that's got a ton of color spread, it might not even be diamond, it might be something like CZ. Why do all diamonds not have the exact same fire? Well, it's because the facet positions are in different locations, and that's going to control our path length. So travel distance, path length, those are synonymous. Now that is A. Let's go to B in terms of optics. I want to talk about the fluorescence of diamond. Fluorescence is a fantastic phenomenon, and it occurs when visible light is emitted. Let's say this way. Diamonds emit visible light when exposed to ultraviolet. Sunlight has ultraviolet, and so sometimes even in sunlight you'll get this weird fluorescence that makes a diamond look blue when exposed to UV light. Other times you just have to have a black light and you're in a dark room, and that's kind of a neat phenomenon. Let me show you an example. This is a brooch, I don't know how you say that, full of brown diamonds at the Smithsonian. And we'll talk about why brown, when you expose them to ultraviolet light, look what happens. Just pick so a lot of them look like they go shades of blue, but there's some, like this one, that goes yellow. Here's a brighter yellow, and here's a big one, kind of just stays dark. This one goes pink. So this is our fluorescence that we see in diamonds. And it ends up being that about 35% of diamonds fluoresce. When the sunlight makes them fluoresce, so UV in sunlight can make them fluoresce. And when that happens, the diamond will start to look a little bit oily. you get this oily appearance in sunlight, and that actually retracts from the diamond's value. When you don't have it making the diamond look kind of hazy and oily, it's just kind of a neat secret that you have in your diamond, and I encourage you to test yours. One of the coolest diamonds in the world at the Smithsonian is called the Portuguese Diamond, and it has some phenomenal amounts of fluorescence. It's a very large stone. It's a 127 carat stone. Well, how big is that? Well, let me show you. Boom. Look how big it is with respect to these people's fingers. And as you see it go fluorescent, it's a very, very pronounced, strong blue color. So we're going to say that, just say that this is the 127 carat Portuguese diamond, which you can see at Smithsonian, where these images are taken from. It's emerald cut. You can see how it's been cut in a stepwise. And legend says it was found in Brazil in the mid-1850s and part of the Portuguese crown jewels. That legend appears to be wrong. It was actually purchased by like a Hollywood starlet in the 1920s out of the Premier mine, which is one of the this is the mine where the Cullinan, the largest diamond ever found. So the Premier mine in South Africa is where this stone was actually found. A fascinating diamond. Almost every big diamond has a story behind it that would be so fun just to talk about. But we don't have time for that. We need to move on. One of the other things that affects optics in diamond is the amount of inclusions that occur in them. These can be very hurtful to their value, right? So this can, let's say that it will reduce monetary value, but it gives many insights into the mantle. So as scientists, we're fascinated by the diamond inclusions, but as gemologists and jewelers, we actually want to reduce them. So what I'd like you to do first is I'd like you to sketch an octahedron, kind of like this one here, and within that octahedron, throw a couple crystals. In this specific example, I suppose it doesn't really matter what they are, but here this would be like a garnet crystal. Garnets come from the mantle. And also here would be an olivine or a clinopyroxene. These are the most common inclusions that will occur in diamonds. Now the most common, so those are three of the most common inclusion in a diamond is graphite, which occurs as black specks. The reason for it is the carbon in the diamond just kind of breaks down along fractures. And you'll get flaky black flecks in your diamond. This is the most likely thing that you'll find in yours. But these are other ones that I can show you some real life pictures of this now. Here's an example of a diamond. It's showing a dodecahedral, somewhat flat and rounded. And inside the diamond, you can see these inclusions of olivine. Here's a more photogenic example. Now, both of these pictures are coming from the Tappert and Tappert Diamond textbook. But here we can see a inclusion of olivine and then a big, beautiful purple garnet. And this would be something that would be so awesome to have inside of a jewelry piece as well. And that occurs more for people who are actual collectors than for the person who's looking for an engagement ring. So let's just say that's that. And I'll see you next time for Diamond Color.